about a concept that is very central to calculations in the science field of chemistry. And this particular kind of calculation is a way for us to really bridge the gap between two kinds of concepts, one being a macro concept of mass, and then the other concept being a micro concept of numbers of really tiny things like atoms or molecules or anything, something like that. So we're going to bridge this gap, and the bridge that we're going to use that scientists have developed is this thing called the mole. And the mole is essentially a specific value of some item, and that item can be anything you want. And that specific value is based off of a concept of the isotope carbon-12. And so it's really defined as the amount of a substance containing the same number of atoms that's exactly 12 grams, that's in exactly 12 grams of the isotope carbon-12. And it turns out that if I were to literally have 12 grams of carbon-12 and I could by hand count every single tiny atom in there, and it turns out that that number would be counting all the way up to this really long number in scientific notation. It's 6.022141179 times 10 to the 23rd. And it turns out that this number is a constant number, and it's really named after the scientist that identified it, Amadeo Avogadro. And so we call this number Avogadro's number. Now, that's actually a really long scientific notation number. We do round it to the third digit or third decimal place, and so it's a 4 sig fig number. So we will use for the rest of this class 6.022 times 10 to the 23rd. And the explicit unit for this is really per mole, or if we put a like 1 over mole, or you could, I've seen it written as like mole to the -1. Okay, so the unit for that is per mole. Now, what what that item is of, how much you have of in a mole is going to change from different calculations to different calculations, and we'll look at that in greater detail here in just a second. Okay, so let's talk about a concept of the mole and how that relates to the mass of a substance. So let's say I do have a mole, a single mole of a substance, and let's pretend my substance is dogs. Okay, and I'm showing one little tiny dog. If I were to take a mole of dogs, which means how many dogs do I have? 6.022 times 10 to the 23rd dogs. That's a lot of dogs. And we put them on the scale. And so let's pretend like I have 6.022 times 10 to the 23rd dogs sitting on the scale. The reading that pops out on the scale obviously won't be 0.00, but the number that comes out is what we will call the molar mass. That's the mass in grams of any particular substance, in our case dogs, if you have a mole. So we're going to call that the molar mass. A really neat thing about chemical substances, so say if we're taking into account this substance of C12H10O6, and we say we have 1 mole of it, or if you want to just go by numbers, you have 6.022 times 10 to the 23rd molecules, right? Molecules of C12H10O6. What will that be in molar mass? Well, it turns out a really neat thing happens is that the molar mass ends up being equivalent to the formula mass, which, yay, we already know how to calculate. Okay, and this is based off the atomic mass units from the periodic table. So we know that the formula mass for, say, C12H10O6 is 250.2 AMUs, and we have calculated that in a previous video. Then, therefore, if this is true, and the molar mass and formula mass are equivalent, if you have 1 mole of something, then it's 250.2, and its mass, so we'll say it's grams per mole. And so this then becomes a really neat, useful conversion factor. And guess what? Where do we use conversion factors? In dimensional analysis. So let's try to use the technique of dimensional analysis for us to convert from mass of a substance here to how many moles of that substance. So again, we're going to start with mass, and we're going to use the mass of calcium chloride, and let's calculate how many moles of calcium chloride will be there based on the conversion factor that we know about calcium chloride is that its molar mass, or formula mass, right, 110.98, and now we're going to say grams of calcium chloride is equivalent to 1 mole of calcium chloride. So that molar mass that we have now extrapolated from formula mass is our conversion factor from the units of mass of grams to moles. So we're going to now start using our dimensional analysis techniques to calculate things in chemistry. So the way we're going to start out is we're going to start with our first value of 5.00 grams of calcium chloride, and we're going to put this over a 1, and we're going to multiply it times our conversion factor of 110.98 grams of calcium chloride to 1 mole. And the unit that you're going to put on the denominator is going to be the unit that's the same on the numerator on the previous fraction. So 110.98 grams of calcium chloride is equivalent to 1 mole of calcium chloride. And we now have arrived at the units that we're wanting to go to. Moles, our grams of calcium chloride will cancel, and we can just do our mathematics here, noting that we need to maintain significant digits. This is 3 sig figs here, and the formula mass, or molar mass if you will, now we do have to take into account its sig figs, and it happens to have 5. So we're doing all multiplication division, so we'll go with the lowest one, and that's 3, and we'll put our answer in 3 sig figs. So I round that to 0.0450 grams of calcium chloride. And that is how many grams? I'm sorry, not grams, moles. Apologies for that. Moles of calcium chloride. All right, so let's try this one more time. Let's do a calculation where we're going the opposite direction from a mole value to a mass value. Now, our conversion factor, the number of the molar mass will be different because we're using a different substance. So the molar mass for nitric acid, which is HNO3, is 63.02 grams, and that would be equivalent to 1 mole of HNO3. And I would make sure that we know what substance we're talking about here. Okay. Now, again, how do you find that? You find that this is going to be the molar mass, essentially the formula mass of that substance. And that's something you're going to have to calculate on your own outside of the problem itself. So what we'll do is we'll start with our number, 2.47 moles of HNO3. Put that over 1. And now we're going to use our conversion factor and convert from moles to grams. So numerator is moles, so we're going to put in moles on the denominator. 1 mole of HNO3 should be equivalent to 63.02 grams of HNO3. And then that we will do our mathematics here, keeping in mind that this is 3 sig figs. This is 4 sig figs. Our answer should then be in 3, and I will round that from my calculator to be 156 grams of HNO3. So there you go. Now, it turns out, because we know that with 1 mole of any substance, based on its basic definition, you should be able to count how many of that thing is there also, whatever item you're talking about. So 6.022 times 10 to the 23rd. This is also a conversion factor that you can use in calculations when you're going to be looking at things like molecules and atoms, because we're starting to get to looking at smaller amounts of things or looking at tinier things. So in addition to using the molar mass conversion factor, we can now use this conversion factor too. So let's do a practice problem where we're going to convert from mass of a substance to the numbers of atoms within a substance. So we're going to start with 10 grams of calcium nitrate, and I want us to figure out how many atoms of oxygen, that means this guy right here, how many atoms of oxygen is in that. So I want you to watch what we do here. So we're going to start with our okay, we'll start that one more time. We're going to start with our 10.0 grams of calcium nitrate. Put that over 1. And we're going to use our basic molar mass conversion of calcium nitrate to moles. And we know that this conversion from mass to moles from previous calculations of calcium nitrate in a previous video is 164.10 grams, which is equivalent to 1 mole of calcium nitrate. And so let's go ahead and do that. So we know that the 164.10 grams of calcium nitrate is equivalent to 1 mole of calcium nitrate. Well, we want to know how many molecules that is in order to get to atoms. So this is where your conversion of moles to amounts in numbers of something takes into account. For every 1 mole of a substance, you know that you have 6.022 times 10 to the 23rd of them. So in this particular case, we can use that as a conversion factor here. So if we say 1 mole of calcium nitrate is equivalent to 6.022 times 10 to the 23rd, and we would say molecules of calcium nitrate. Now, why am I saying molecules? Well, that's because this whole thing is a molecule. Okay. Now, if we want to go from molecules to atoms, really the only thing we do is look at the formula of the molecule itself. So if we have Ca and NO3 in parentheses 2, I need to know how many total oxygens is in this one molecule. So I have 1 molecule of calcium nitrate. Well, how many atoms of O, or oxygen, is there? Well, you take the 2 and multiply times the subscript 3, and that tells you 6. So this is a conversion factor right here, guys. 1 to 6. So for every 1 molecule of calcium nitrate, that's equal to 6 atoms of oxygen. And hey, we're at the point of calculating the thing that we're wanting. So multiply all the numerator together, divide by all the denominator, and you put your answer in 3 sig figs based on the 10.0, and you get a value of 2.20 times 10 to the 23rd atoms of oxygen. Okay, so there's your answer. It's possible to go backwards. On that kind of problem, we can start with atoms and go backwards into mass. So let's try a problem like that. This one we have a value of atoms of hydrogen, or H, that happens to be in this substance, that molecule. So how we start this out is we're going to do the 2.75 times 10 to the 25th atoms of H, and we're going to put that over 1, and we're going to convert those into molecules. And so again, you have to look at the formula for that. So for every one atom of H and how that's equivalent to 1 molecule of H2O, well, if you look at the subscript here, it's actually for every 2 atoms of H, it's equal to 1 molecule of H2O. So what we'll do is we'll write 2 atoms of H is equal to 1 molecule of H2O. And at this point, we can now move to going from molecules to moles. And this is Avogadro's number related to 1 mole. 6.022 times 10 to the 23rd is equivalent to 1 mole of any substance. So here we go. For every 6.022 times 10 to the 23rd molecules of H2O, that's equivalent to 1 mole of H2O. And for us to go from converting moles to mass, we need to know the molar mass conversion, and that's the formula mass in grams of H2O, which ends up being 18.02 grams is equal to 1 mole. So we'll say for every 1 mole of H2O, that's equivalent to 18.02 grams of H2O. And we'll stop there. All the rest of the units cancel out, leaves us with grams of H2O, which is what we were looking for. And when we multiply all the numerator, divide by all the denominator, putting that in 3 sig figs based on our initial number, that ends up being 411 grams of H2O. There you go. All right, so those are 4 classic examples of how to do conversions between mass and atoms and molecules and the mole, relating the mole to that. I highly recommend you guys practicing some more example problems. There are some in your homework in the back of your chapters, and we'll do some more in class. I will see you next week.